Okay, just what's the fastest way of doing this? Yeah, I mean, if you see these two here, have the same variables, so we have two equations with two variables, the b and d. So if let's say we subtract the one from the other, we have that, let's say you subtract this from this. So let's do it here. Sorry. So we have 2b plus d is equal with 1, and then we'll have let's say minus b minus d is equal with minus 1. So now if you add them together, that should give you b is equal with 0. So b is equal with 0. That means that if you go here and you put b equal with 0, gives you that d is equal with 1. So we have b and d. So now we want to find a and c. So since b is equal with 0, that means that a from this here, that means that a is equal with 1. And since a is equal with 1, that means that so yeah, we have 2 times 1 is 2, so that means that c is equal with 0. So a1, c0, b0, d1. So that means that we can go here and replace the b with, we replace a and b, c, d. So we said a is equal with 1, b is equal with 0, so we can take it off. And c is equal with 0, so we take all this off, and d is equal with 1. So all these things here can be written as x over x squared plus 1 plus 1 over x squared plus 2. So, and now instead of finding the integral of this, we find the integral of what we have here. We can erase the rest. For this here, we can go directly and substitute it with, you remember the formula that I gave you in the beginning, that the integral of 1 over x squared plus a squared with respect to x is equal with 1 over a times the inverse tangent of x over a plus c. So that means that here we have that this here you can write it as the x squared plus square root of 2 squared. Okay, so that means that your a in this case is square root of 2. So that means that the integral of this here, it should be, according with the formula, it should be 1 over square root of 2 times the inverse tan of x over square root of 2. So that's the integral of this. And now you have to find the integral of this, which is it's nothing difficult, it's just a simple integration by substitution. So if you substitute wherever u equal with x squared plus 1, that means that du over dx is equal with 2x. So, and I always like to solve here for dx. So that means that dx should be equal with du over 2x. And now if you go back to this integral here, let's finish it here. So we have the integral of x over x squared plus 1. So this we write it as x. Wherever x squared plus 1, we put the u. and wherever the dx we put du over 2x, so this cancels with this. So now the integral of this with respect to u, it's we bring the 1/2 outside, and the integral of du over u is ln of u, which in our case it will be 1/2. We go back and we substitute the x squared plus 1, and that should be ln x squared plus 1. Of course, you don't need the absolute value anymore because this is always positive. That's about it. So that means that if we go here and we just substitute this here, 1/2 ln x squared plus 1 plus, we said this here is the integral of this, and of course plus c. Yeah, do one which is, let's say, as more complicated as it can be. Let's find the integral of 2x plus 1 over x plus 1 in the third plus, times x squared plus 4 squared. And of course with respect to x. Okay, so like of course the degree of the numerator is 1 and the degree of the denominator is 3 and 4 here, so it's 7, so that means that we don't need to do a division of polynomials. I mean, this here, it's why I decided to do it is because it's as complicated as it can be. What do I mean by that? I mean, what you have here, you have this here, which is a linear factor of x plus 1, but it's in the third power, and then you have this here, which is a quadratic factor, because you know the x squared plus 4 we cannot break it down because its discriminant is negative, so this is a quadratic again in the second power. So now let's forget about again the integral, let's just work on the rational function. So you have to write this as okay, a over x plus 1. Now, you remember that when you have it in a factor, linear or quadratic in a bigger power than 1, you have to include all the powers. So that means a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 to the third. So we're done with this. And now, the same thing for here. But here, excuse me, this is just the plus. Continue for here, from here. So this will be a, b, c, d, x plus e over x squared plus 4. Because, you know, now it's quadratic, so the numerator has to be linear. And have to take it one more time because it's in the second power, so this will be fx plus g over x squared plus 4 squared. So that's about it. So you see here that it becomes not more complicated, but it's more work because you have to find 1, 2, 3, 4, 5, 6, 7 unknowns, but that's okay because I assume that we will get as many equations. So just we have to go and do a little bit operations. So I mean, of course, this is the least common denominator. So we have to multiply everything by the least common denominator. So that means that when you do that, here, what it will be left, it will be the x plus 1 square times x square plus 4 square. Now, if we go here, what it will be left, it will be b times, okay, if you multiply again with all this, it will be b times x plus 1 times x square plus 4 square. You do this here, multiply the least common denominator with this here, so that means what it will be left, it will be x plus 1 square times x plus x square plus 4 to the first, because we already have the 1 here. So, and finally, and of course times dx plus e. And finally, we have this here, so that should be fx plus g times the, if we multiply by the least common denominator, then this will cancel with this, and we'll only be left with x plus 1 to the third. I will not solve it completely, so I will not find all these A, B, C, D, E, F, G, but I just did it because I wanted to show you how you break down the polynomial when you have that the powers of the linear and the quadratic are greater than 1. So thank you for taking the time to view this video, and I hope you find it useful. Bye for now.